Alright, hello everyone. Welcome back to another video for regression analysis. This week we are going to finish up chapter 11 with talking about section 6 through 15. So the section 11.6 talked all about collinearity and variable selection. So there are two situations in variable selection procedures. The first one is with predictor variables are not collinear, which means they show no strong evidence of collinearity. And the second is when predictor variables are collinear, so the data is highly multicollinear. So if the data is collinear, we proceed one way, and if the data is not collinear, we proceed a different way. The first step should be calculating the variance inflation factors for the variables. If none of the values are greater than 10, then collinearity is not an issue. All right, so section 11.7, we're going to talk about evaluating all possible equations. So the first procedure explained applies well to both collinear and non-collinear data. The procedure involves fitting all possible subset equations to the body of data. And the total number of fitted equations, just like we spoke about in class last week, is equal to 2 to the q power, where q is the number of equations fitted. And our y sub I hat is equal to our y sub bar, which is found from fitting the model y equals beta sub 0 plus epsilon. So the most efficient way to pick the best equations is when we have a lot of equations. The most efficient way to pick the best equation when we have a lot of equations is to find the best equation containing a specified number of variables. These regressions are then analyzed for outliers, autocorrelation, or the need for a transformation before approaching our final model. Certain shortcuts can be used when the numbers of variables is exceptionally large. So, like we have seen in studies before, that these variables can become a lot, and we can have a lot of variables. So there's certain things and tactics we can use in order to try to cut down on the number of variables we have, which will then allow us to go about solving and coming to conclusions more efficiently. Great, so section 11.8, we're going to talk all about variable selection procedures. So discussing cases when there are a large number of potential predictor variables, variables are either introduced or deleted one at a time. So when we have Q equations, these procedures will involve the evaluation at most Q plus 1 equations. So we're not going to be dealing with the large number of equations we had when we were using the 2 to the Q. Instead, we are going to be using Q plus 1, which is going to give us a lot smaller set of equations, which is, like we've seen, is easier to work with when we have a small number of variables and equations. So we have 3 different methods of variable selection. The first one is our forward selection procedure. So in this case, we're going to start with an equation containing no predictor variables. The first variable introduced is the one with the highest simple correlation with response to the variable y. If the regression coefficient of that specified variable is significantly different from 0, then the variable is going to be retained and we're going to move on to our next variable. And this procedure is kept on going until the last variable entering the equation has an either insignificant regression coefficient or all the variables are included in the equation. And in order to find our significance, we're going to use a t-test in this situation. So the next method is going to be the backwards elimination procedure. So in this case, we're going to start with a full equation, and then see if we can drop one variable at a time. Variables are dropped on their contribution to the reduction of the sum of squares. The first variable that is deleted is the one with the smallest contribution to the reduction of the error of sum of squares. So this is equivalent to deleting the variable with the smallest value from our t-test. If all the t-tests are significant, then all the variables are retained. The procedure is complete when all the t-tests are significant or all the variables have been deleted. And our third method is going to be our stepwise method. So this is essentially a forward selection procedure, but with the added possibility of deleting a variable down the road. So a variable entered in earlier stages can be deleted in later stages in this method. So our AIC and our BIC can be used for setting up stepwise procedures. This procedure differs greatly from procedures based on the t-statistics. So we're going to use our t-statistics again in this procedure in order to try to add or delete variables. So our stepwise method is kind of a combination between the forward selection and our backward selection, as we can both add and delete as the time goes on. So 11.9, we're going to go over general remarks on variable selection methods. So we're going to use the above selection procedures that we talked about in section 11.8 with caution, and they should not be used mechanically to determine the best variables. So like we talked about before, we have a few ways to know when we can stop the procedures, but in this section, we're going to really cement the rule of when to stop. So our stopping rule for our forward selection is to stop if the minimum t-test is less than 1. And our stopping rule for backwards elimination is to stop if the minimum t-test is greater than 1. So our textbook recommends backwards elimination over the forward selection procedure due to the fact that we are starting with our full set of variables for inspection, even if we don't use it for the final equation. Backwards elimination is also better to use in situations with collinearity. So they suggest, again, the backwards selection just because we can see all the variables we're starting with right away, and we're not trying to guess what some of the variables might be if they're not there, like in forward selection when we're starting with no variables at all. So section 11.10 is an example of this using the supervisor performance data like we've seen in past videos. So we're looking at variable selection procedures for the supervisor data, which is a non-collinear situation. So the VIF values show that the collinearity is not an issue since we have a range of 1.2 to 3.1, which would indicate that collinearity is not an issue. So in this case, they showed both forward and backward selection. So table 11.2 right here is going to show forward selection first. So for the rank column, this is the rank of the subset obtained in forward selection relative to the best subset of the sample size. That's this column right here. And our P column is the number of predictor variables. So we know this is forward selection since we were starting with a smaller number and increasing as the time goes on. So the stopping rule used in this example were to stop if the minimum absolute t-test is less than our t-value of 0.05 with n minus p, and to stop if the minimum absolute t-test is less than 1. So we're going to use t with an alpha value of 0.05 and our statistic of n minus p. So the first rule terminated with the variables x1 and x3. The second rule terminated with the variables x sub 1, x sub 3, and x sub 6, and so on. So they also showed backwards elimination in this case by table 11.3. And again, we know this is backwards elimination since we're starting with a bigger set of variables, so all the variables, and then we're decreasing as the procedure moves on. So this table is an identical structure to our forward selection procedure with the same labels. And the stopping rules in this case were to stop if the minimum absolute t-test is greater than our t-value at an alpha of 0.05 and a statistic of n minus p, and to stop this equated to stop if the minimum absolute t-test is greater than 1. So just like forward selection, the first stopping rule in this case selected variables x1 and x3 as well. And the second stopping rule selected, again, x1, x3, and x6. And then they were able to find this equation right here at the bottom, which represented the data in this case. And then just another side note, they also have come to the conclusion that the Mallow statistic is not useful in this case. So section 11.11, we're going to discuss variable selection for collinear data. So the textbook recommended a different set of procedures for selecting variables in analysis of collinear data. Methods we already discussed can be used with a small number of variables, but not with a large number of variables. And obviously, when in the real world, there's not going to be tests that have small numbers of variables most of the time. So two different approaches can be taken when we have large numbers of variables with collinear data. The first is to try to break down collinearity by deleting variables. Once the collinearities are identified, a set of variables can be deleted to produce a reduced non-collinear data set. And the second approach is to use ridge regression. But in the textbook described that the first approach is almost always used. All right, so section 11.12 is going to be another example of this, but using data from a homicide source. So this data was from Detroit and is collected in the years of 1961 to 1973 on the role of firearms in accounting for the rising homicide rates. So table 11.6 here is going to, going to show all our variables, the numbers associated with the variables, the symbols, and a quick description of each variable. So the purpose of the predictor variable, the purpose of this example was used to show the danger of mechanical variable selection procedures in collinear situations. So the model they used for this case is represented by H for homicide, and that is going to equal our beta sub 0 plus our beta sub 1 times our G variable plus our beta sub 2 times our M variable plus our beta sub 3 times our W variable plus our epsilon. If the standards assumptions hold, we would be able to terminate G, which has a t-value of 0.68. All right, and we can find this from table 11.10, which shows the three variables we used in the model, the coefficients, and the t-test values associated with them, and then our R-squared adjusted down at the bottom. So from this table, G is selected by forward selection since it has the largest t-value, then followed by M, then followed by W. The dramatic change in G between models A, D, and F show us that collinearity is indeed a suspect in this case. If we did backwards elimination based off of this table, the first variable to leave is G, and then both M and W have significant t-tests, and the procedure terminates. So in this case, we can see that forward selection and backwards elimination gave us two completely different sets of variables. So G was the first variable selected by forwards selection, but it was also the first one eliminated by backwards elimination, which is why this does not work with collinear data. So this is a perfect example to show us that we really can't trust these procedures when we have data that is collinear. All right, so 11.13, we're going to discuss variable selection using ridge regression. So the one main goal of ridge regression is to produce a regression equation with stable coefficients. So the objective of a good variable selection is to select a set of variables to provide a clear understanding of the process being studied and then formulate an equation that provides an accurate forecast of the response variable corresponding to the values of the predictor variables not included in the study. The guidelines for elimination using ridge trace are outlined on the screen. So just quickly, the first one is to eliminate variables whose coefficients are stable but small. The second, we're going to eliminate variables with unstable coefficients. So unstable coefficients that tend to 0 in this case. And then the next one is going to be eliminate one or more variables with unstable coefficients again, and the variables remaining from the original set are going to be used in the regression equation. Right. So section 11.14 is another example, and this time we're going to be going over selection of variables in an air pollution study. So the study relating mortality to climate, socioeconomic, and pollution variables. Again, if we take a look at table 11.11, we have all the variables included in the study, quick description of each variable, along with their mean and standard deviation. So we have 15 predictor variables in this case and one response variable. So evidence of collinearity was indeed found. The smallest t-test values do not necessarily mean that the variable is not important when collinearity is present. So like we saw with the homicide data, collinearity kind of messes up all our assumptions and all our thinkings. So we just have to take that into account when we do have data with collinear nature. So from the first criteria that we talked about before, variables 7, 8, 10, 11, and 15 are eliminated. From the second criteria, it was shown that variables 12 and 13 are eliminated. So after this step, collinearity was proven to have disappeared. In the study, the third case was not needed. So this study just did a quick example of how to eliminate the variables when we have collinear data. They didn't really go into too much more after that. Right, so for section 11.15, this section talked about a possible strategy for fitting regression models. So this, they just ran through a quick steps to fit a regression model. And they also noted that it was important to know that there was no correct approach in this case. And this is simply just an example of many different ways that you can do it. So we assume we have a response variable y with variables x1 all the way up to xp. And we have a large set of variables, and we want to end up with an acceptable reduced set. So on the screen, we have a possible set of steps. The first step, we're going to examine our variables one at a time. We're going to look for skewedness, outliers, and perform necessary transformations if needed. Then we're going to move on to make scatter plots of the variables. We're going to delete redundant variables if we have any. And then we're going to move on to fit a full linear regression model. And then we can then delete variables with insignificant t-tests. So for reduced models, we're going to examine the residuals for linearity, heteroscedasticity, autocorrelation, outliers, high leverage points, and influential points. We're then going to move on to examine the need to see if additional variables can be dropped. We're going to examine if new variables also need to be brought on in this step as well. And then we're going to move on to, for the final fitted model. We need to check the variance inflation factors like we've seen earlier in this video. And lastly, we're going to attempt to validate the fitted model. So like I said before, these are just some suggestions of steps, and they can be altered based on the study and what you're looking for and what the outcome is and what the data is and all that stuff. Right. And then section 11.16 was just a little bibliography where they referenced other books that discuss this material. All right, so thank you guys again for listening. As always, any questions, just let me know, and I'll see you next week. Thank you.